what's going on, guys? Comic here. Last video we've been playing around with a boot sector game, so we've managed to run that game on an emulator, on 2 emulators to be exact, and also we did create a bootable USB flash drive. We've written that game onto a flash drive and successfully boot on a x86 real hardware on my old Asus laptop in particular. And we were able to play Tetris with no operating system dependencies at all. That when that Tetris was actually running from the boot sector. But a very reasonable thought comes into mind, and the thought is: so if we want to play boot sector games, doesn't really mean that every time we need to create a new USB flash drive and write the image there. So let's say we have 10 games. In that case, we'll need 10 USB flash drives, and in order to change the game, we need to reboot our computer to plug in another USB flash drive. So it's not the most efficient way ever of doing things. So I was thinking, what if we try to make a simple, well, I don't really want to call it an operating system, but technically it might be treated as an operating system. Some sort of a environment that would allow us to run boot sector games without a need to restart the computer. So the idea is very simple. We just want to load the images. So we have a single I'm using the floppy image, even though I'm writing that to the USB flash drive, but the size of that image is equal to the floppy image. That's why I call it floppy image. So there shouldn't be any confusion. Like, so I'm talking about the floppy image, but that floppy image is going to be written on the USB flash drive. And when it comes to reading those games from the flash drive, we're going to be treating them as the device, the USB flash drive, is treated as the hard drive, not the floppy disk. So there might be some misunderstanding in this kind of like terminology, let's say. But anyway, so if we have some sort of a menu that would allow us to pick a certain game and then load that game back into the boot sector and run it, and then when the game is over, we want to drop back to our menu. So that would be the exact environment that I'm talking about. So imagine that you have a menu where you can just pick a certain game and run it. And meanwhile, it means that the game on its own, the boot sector game, can run independently from this. So you can just create, it's still no operating system dependencies, it's still absolutely standalone, but you can pack many games onto a single flash drive. Okay, and then you just can select which game to play. So this is the exact project that I'm currently working on, and I'm going to be making a set of tutorials on how to deal with that. And the very first thing to consider, so what we could have actually, no, we can't, we could have created the menu just right in the boot sector. There is enough space for that. But the problem is that in that case, the games that we're about to be running would no longer be capable of running in the boot sector. They should be running on somewhat a different sector. And even though for most games this should be fine, and I've been testing that as well, but still, I just really want the games to be running in the boot sector as far as they are the boot sector games. I don't know, just feel that would be a better way of doing things. So for that purpose, we need to put our menu somewhere else, but not to the boot sector. And in order to do this, we need a program that is known as the bootloader. So bootloader is a piece of code that would be loading our menu from the image. And again, let's just deal on the terminology. So when I'm going to be referencing the image, I would be saying floppy image because it's 1.4 megabytes size. But this floppy image would be written to the USB flash drive. Again, and the USB flash drive from the BIOS perspective is going to be treated as the hard disk drive, not the floppy disk. And when it comes to reading the sectors, we're going to be using the specific codes for writing from the hard drive, not from the floppy drive. But again, I don't want to call it the flash image because in that case it would be just reasonable to have the size of that image as the size of the flash, of the USB flash, but we don't really need this 2 gigabytes. I have the 2 gigabyte flash. We don't need that, and it's more than enough to have a floppy drive size of the image. So let's just deal just a bit of a convention here. So I'm gonna be calling the image like the floppy drive image, the floppy image, but when it comes on the real hardware, it would be working as the hard. So the USB flash drive is going to be treated as the hard drive, which it is from the BIOS perspective. So I hope that's clear, and I'm not going to be coming back to this any longer. So I hope it's clear. Okay. So now the bootloader is the program that would load our menu somewhere to the memory, right? I already know where exactly. That's another big topic. But anyway, just to give a general plan of what we're supposed to be doing. And then it would jump there. By saying jump, I mean the jump instruction, which would result in the code of our menu is gonna get executed. And then we would be able to pick up the certain game, and that's kind of it. But before anything else, and before actually implementing the menu itself, which might be a bit of a pain later on, the very first thing to consider is we actually need to write the bootloader. And before actually having a menu, we would have just a string to load from the floppy drive to the memory, like a placeholder of our future menu. But even that is a bit too much for a start. So the very first thing that, and what we're going to be doing in this video, we're going to just create a boilerplate bootloader code and try to compile and run it on emulator to see how it works. And the only function it would be having is the print function. But the code is not the major issue when you're coding in assembly, because it's not about the different language, it's about absolutely different way of how you think. And I don't know how for you guys, for others who had experience with this, but for me personally, this x86 bare metal assembly programming is all the matter of understanding the memory addressing and the registers, like which register is responsible for what, and how the real mode. So again, like, so we're just, so before writing the code, I just want to give you a bit of an understanding of the environment that we're supposed to be working within, because without that understanding, it doesn't make any sense at all. And if you just copy paste the bootloader codes from the tutorials, and by the way, they differ from time to time. You might have no idea why in one tutorial this is done like that, like this, and in another like that. So it might be done in different ways depending on what goals you have, on kind of what goals you set up. So I would try to highlight every single line of code, every single instruction within the bootloader, and why exactly it's done this way and not another way, just to make it clear in regards to the dependency between the way how to write these instructions and how this corresponds to the eventual goal that we have in mind. So I hope that's clear. So before anything else, the very first thing that we need to know is our memory and how is the memory layout. Okay, so there are two types of memory that we're supposed to be working with. The first one is RAM, which stands for random access memory. This is the operating system memory of the computer, and when the computer boots, it's specific to x86 processor architecture. It boots to so-called real mode, which gives you limitations in regards how much memory you have. I'm sorry, just don't remember exactly that number, but all this can be found. Yeah, by the way, let's search for real mode in a very nice resource called OSDev. Okay, so here it is. So if you want to learn more what the real mode is, I highly recommend to read through this article, just to give a general idea, because if I just start explaining about this, it just takes ages, so I don't really want to doing that. And anyway, what we need to know, what is specific to this real mode, is how the memory layout is operating. So here I've selected only 3 lines, and let's better start here. So here is the most essential table that we need to know in regards to real mode memory addressing. So let's quickly walk through the most essential parts, and then okay. So this sort of a thing. So the exact physical memory address of 7C00 is exactly the place where the code should be in order to make your processor start executing your code. I'm not 100% sure, but I guess that the register that is known as the code segment is pointing to this exact location. I might be wrong in the details. I'm sorry, guys. I'm not 100% sure how this works, but anyway, it's kind of like if we just whatever code we have here at this location, it's going to start being executed. That's the most essential thing to consider, and it takes only 512 bytes, and we have a specific boot signature there on that sector. For otherwise, if that signature is not available, it's not going to be working. But we'll talk about this later on when we're going to be writing the code. So this 512 bytes is the place where the bootloader works. And when we're talking about the boot sector games, the boot sector game is loaded here as well. So later on, when we're going to be developing our own boot sector games, this is going to be really handy. But for now, let's move further on. So below that, we have around 30 kilobytes and I'm not sure about. Sorry, I don't know how to read this. So we have the memory below this, and we have the memory above this. And this memory is what is known as the usable memory. So we can use this memory to create our own so-called real mode operating system, which the one that we're developing might be treated as the real world operating system technically. Okay, so now another important thing. So here is an interesting part, which is the video memory, but we're not going to be touching this, at least in this tutorial. And another important thing is this one, interrupt vector table. So we have a set of extremely useful kind of like pre-existing, let's call them methods from the high level programming perspective. This might be treated as functions, so some sort of a functionality that allows to do very basic things like draw the character on the screen, or read a single character from the keyboard. So or for example, read a sector from the floppy image, or from whatever, from the image that is written to your storage device. Okay, so things like dealing with the hardware, like again, like this print and stuff, hardware like the keyboard, listening to keyboard, like taking the user input and just like working with the hard drive, with the USB flash drive. All this is possible using this specific functionality, and we have the list of this bias specified functions here, and we're going to be referencing it a bit later when it comes to implementing the print function. Okay, we're going to be using this 10A, this one 10H in particular, this one, yeah, character to write. So we're going to be using this one. Okay, so now let's get back to this schema here. So we have the bootloader, which would be loaded exactly at this physical memory address. Okay, and then I will probably get rid of stack for now, because we're not going to be using stack at least in this video, and there are some thoughts about the stack which probably just make it in a separate one. There would be just too much of information. So and also this placeholder data, again, like for this tutorial, it's not needed really, so we can just get rid of this as well. So in this video in particular, the only random access memory territory that we're supposed to be using are 512 bytes from here and up to here. But yeah, and also when it comes to, like here I have the extended version of the memory map, but for now we actually want to reduce it to this sort of a format, because we're going to be using writing the only sector. In this video we're going to be writing the only sector containing the instructions, the compiled instructions like machine code for our bootloader to the floppy image that would be then written to the USB flash drive. Well, I'm not going to be writing this to USB flash drive in this video. I will show this a bit later. I've been testing this already, works, but the real hardware demonstration is not going to be available in every video because it just doesn't make sense. But then later on we'll have a bit more interesting things to have a look at. I'll make a video with the hardware demonstration, probably even just like a separate one. Okay, so this is pretty it. So we need to do two things. We need to write the code for bootloader, and then we need to create an image that is going to be used by the emulator in our case first, and later on this image would be written to USB to the USB flash drive. And the way of how to create that image is exactly the same to what we've been doing in the previous video when we were creating a bootable image from the Tetris game. So I hope this is clear, and now without further ado, let's actually start writing some code. So here I have the file called boot.asm. This is here is our bootloader code is gonna be living. Okay, just yeah. So okay, let's just start writing some code. So first we need to say bit 16. So yeah, by the way, I'm using the NASM assembler, which stands for Net Wide Assembler. It's free, it's available on Linux. If you want to run this on Windows, this might be done in the DOSBox. You need to install the DOSBox emulator and then install NASM there. So that's the way how to go. And again, like most of these amateur operating systems are written using NASM, as well as the boot sector games. So if you're really about doing all of this stuff, you really need to be well, it's much easier to do on Linux, but on Windows you really need to take a bit more effort to set up the environment. Okay, so the very first thing, we need to give NASM an idea that we're working with a 16-bit code, because by default it's the 32-bit code if I'm not mistaken. So we say tell NASM to work with let's say to assemble 16-bit code. Okay, I really hope that. Sorry guys, just hold on a sec. Sorry, I just was checking out the spelling of how the assemble is spelled. Okay, so the next thing is the origin. So as they call it, a hint to the assembler of where our code starts. So this is the boilerplate code, so it's available everywhere. So we can simply say org, and then this memory address that I've been talking about. So starts from 7C00. But to define this, we need to say 0x7C00. So say tell NASM the code is running at boot sector. Now, how this affects the overall stuff. So in assembly we have things like labels. So let's say we can say label, and then print whatever assembly instruction. And this label is gonna be so if we want to jump to this label from somewhere, this label has a very specific physical address. And in order to make NASM encode this specific physical address properly, we need to know the origin of where we start from. So if I'm not mistaken, that the data segment is the guy who's responsible for addressing for data that we're supposed to be using. So if we don't specify this properly, it would be it would just collapse because the labels would not match the actual data that we want to reference. So I'm sorry for this weird understanding. I'm still learning about this, so I have some understanding, but it's not clear enough to talk about this in great details. But I just really want to try to cover as many things as I can. So anyway, so then we have another 3 boilerplate instructions. So we need to say move AX 0, which initializes AX register to 0, and later on I'll introduce how to make. So this, by the way, this takes 2 instructions if I'm not mistaken, and later I'll introduce the way how to use how to use the only instruction. This is going to be incredibly useful for writing boot sector games, just to save bytes, because the more bytes we save, the more space we have for our game logic. Okay, and now we want to set up this data segment register, as I've been mentioning, and we're resetting this to 0, and it would be like from here, and then it just gets calculated properly. We can't do like this because it's just not going to be working. It's not legal instructions, so we can't access data segment directly. And AX is just the accumulator register. So, by the way, so it's absolutely essential to. So here you can read about the data segment. So stores the starting address of the data segment as well as the complete data, and regarding the registers itself. So AX is the accumulator register, so usually used for arithmetics, logics, etc. So it's like really like for arithmetics, it's really useful. But in this case, we use the AX register just to. So it's like if we think of this from the object-oriented programming perspective, then we can say that DS is private while AX is public. So AX can be initialized like from the constant or from the memory from somewhere, and DS can only be initialized from the other registers. So that's the way to go. And here we want to move ES and 0 as well. So ES stands for extra segment, and here it is. It's if program needs to access second data segment, it can use the second segment register. So it's a question whether the program is going to be doing this or not, but smart guys really recommend to initialize the segment registers, segment register as well. So okay, so here we just want to init segment registers. So the data segment and the extra segment. I could have, well, I just don't really want to comment every single line of code where it's not needed, but well, probably we can go for this. So let's say at least we can learn, at least in this way, we can learn about the names of the registers and what they mean. So, you know, like I've been coding in assembly around a couple of years ago, and I completely forgot everything, believe it or not. So making this detailed commentaries is good for your future self. If you just don't code in assembly for some time and then you get back, it would be nice to see this commanded code, so at least you recall what that means. So let's say set accumulator. If I only knew how to spell the accumulator properly. Accumulator, let me just copy paste this better. Set accumulator register to 0, and set data segment. So let's call it, let's go in from, it's probably accumulator register to 0, set data segment. I want them to be capital to give the names for these guys. Set data segment to 0. Okay. And then here we want to set extra segment to 0. That's pretty it. Segment to 0. Okay. And now at the very bottom of the file, so we need to make sure that the last 2 bytes of the boot sector of the eventual code that would be uploaded to the memory, there should be a so-called boot signature, which is word of hexadecimal AA55. So this is just a constant. So this is the boot signature. Okay, so we can say set boot signature. And another a bit, I would say, a bit misleading probably, or confusing thing about assembly language, that the code which results being compiled into processor instructions, the machine code, and also the data are bundled all together. So we just have them in a single file, and we have instructions, and then right after instructions we have the data. So you need to be very careful with this and not get confused by this. But if we leave it just like this, in this case, sorry, not word by DV, obviously defined word. Yeah. In this case, well, let's actually compile this, so I could give you a visual idea of what's going to happen. So let me just open the terminal in the current working directory. Okay. All right. And yeah. So to compile this, I need to say nasm -f bin for binary, and then this boot.asm -o object file boot.image. Okay, so now we have our boot image appeared here, and I'm using XXD, which stands for which is the hexadecimal viewer. So it's the utility to see the to inspect the binary output, to see the binary files in the user readable format, let's say, not in ASCII, but in a hex format. So boot.image, and here we can see the bytes. So here we have the bytes for our code being generated, right? And this I don't even know. Hold on a sec. Yeah, so it's definitely at very least we can say that this is not 512 bytes long, and if it's not so, it's not going to be working. So we need to make sure that the entire executable, so now we're talking about the executable, this boot image is the binary image, but it would be executed later on. Anyway, the code stored here is going to be executed. So probably, well, probably just for clarity, we will call this bin. Okay. Yeah, like this, bin. And now just remove this image. So rm boot.image. Okay. So this is going to be a binary executable. Okay. So here's what we need to do. So here is what we need to do to fill, let's say, trailing zeros to get exactly 512 bytes long binary file. Okay, and here we can simply say times and 510, because minus these 2 bytes, minus, and this means here, like the current address, minus, I'm not sure whether this is the starting address, but well, logically it should be like from, well, generally what this does, it just takes, so from all the bytes that we already have, starting from the very last instruction, so we need to add this 0. So here we say just define byte 0. Okay, so fill trailing zeros to get exactly 512 bytes long binary file. Okay, and if we run this again and inspect with XXD, yeah, bin. Now you see, like, oh, I'm sorry guys, I've missed the NDNS, so this should be or hold on a sec, it's another important thing. Okay, just hold on a sec. Okay guys, I'm sorry, it was correct the first time, AA55, but when we assemble this and inspect later on, we have the order. Now the order is different. We have 55 here and AA here, and this is because of what is known as NDNS. So the byte NDNS, you can search more for this. I'm not an expert to give the detailed explanation on what is that, but anyway, this is the boilerplate code, so you don't really need to write this every time. You can just copy paste this boilerplate code from your previous sources, and I'm not going to be explaining this later on. I will just be saying I'll start with my boilerplate code, and I just want to explain it once, and that's pretty it. So I hope that's clear. So now already this should be capable to boot actually, but we're not printing anything, we're not doing anything, so we can't just verify that great if it works or not. So let's define a function that would be printing a string for us. And first let's define the string on its own. So here it would be the section with the messages, and here we say success message, and then we'll have an error message, but that would be the topic of the second part. So success message, and I want to define byte, and now I can just provide the string. The string should end with a trailing 0, because it's not trailing, just with a 0. And here let's call our operating system GameOS. Seems reasonable. So GameOS is loaded. That's pretty it. And now we want to create the procedure. I hope I spelled this properly. Sorry guys, just need to check this out. I want to avoid any spelling mistakes. Procedure. I'm not a native speaker, so yeah, I'm not that great in grammar. So procedure to print a string. Okay, so let's call it print string. Okay, and this is the label, so we're going to be jumping here in order to no, it's going to be a function. We're going to be using the call. No, we're not going to be using jump, we're going to be using call. Okay, and now again, like here are a few things that we need to do. And the very first thing is we need to clear the direction flag. And you might be wondering what the heck the direction flag is. So the direction flag, so CLD cleans the direction flag and is used to influence the direction between some of the instruction will work with this wrap prefix. Okay, here is a very nice question on Stack Overflow. So the guy is not capable of understanding what it is and how it works, and I will just link. I'll just put a link in the description below this video, so you can read about what the direction flag is. But in our case, we don't really need to understand much what that means, and the entire print string function might be treated as the black box, so you don't really need to understand that much what exactly is going on there. But here I just say clear direction flag. Okay. And then in order to actually being able to print a single character, so let's start with a single character, we need to use this. So I just don't need this, no, I just don't want to close to not let's lose the links. So in order to print the string, there is a BIOS interrupt called 10H, and it's available in the interrupt vector table. So in this address in the RAM, it's available there. It's like hard-coded to BIOS, if I'm not mistaken. So we need to, in order to print, it serves different purposes, and among others, it serves the purpose of printing strings, like printing as a single character. So we're going to be using what is known as the teletype output, and in order to make use of this call, we need to make some sort of a setup, starting from setting up the H register. And then when it comes to using some pre-built BIOS functionality, The matter of specifying specific registers, it can be explained why exactly we use these registers or not somewhat another registers, but it's just predefined by the BIOS itself. So the documentation states that you need to set up certain particular registers to certain values in order to make this BIOS codes working properly. So this is just an idea where you can get the information. I'll give the link to this link in the description below the video as well. So in order to print, oh my god, in order to print, the very first thing we need to say move AH and this constant of hexadecimal OE. Yeah, like this. Oh, I'm sorry. What have I done? 0E, not OE, 0E. Sorry. So here we want to enable teletype output for int 0x10 BIOS call. Okay. Interrupt, probably let's call it. Let's make it like this. So I really love to put a bit of documentation into the source code because it's really hard to manage, like to keep track of all the source documentation. But when you're doing repetitive things within your code, it's really nice to put all this essential important documentation statements directly into the code. So later on you can just read through the single source file and recall all the documentation, all the important documentation points that you need. Okay, so now we need to create a bit of a loop here. So I'll create a label called next char, which stands for next character. We're going to be jumping back and forth until we complete this stuff. And now the next instruction is called load single byte. So what this instruction means, so again, I'm explaining this only once. Later on I would be using this print string just as a black box, and I would be explaining only those functions that would be implemented from scratch, because otherwise these tutorials would take ages. I'm not, it already takes too long, but it's all really important. So what the load single byte is, it's a shortcut, so it might be done in a more, so load single byte is 1 byte instruction, right? It might be done in more steps, but this one is the shortest one, and when we're coding the boot sector stuff, it's really a good idea to use as minimal amount of bytes in the eventual executable as we can. So it literally reads a byte. It reads byte by byte in this SE register. And by the way, the order of how it reads, like back and forth, like from one direction to another, I'm not sure how exactly, but this somehow it deals with this direction flag. And one of the reasons to clear it is just to make sure that we reading this SI register in a proper order, for otherwise we potentially might be reading this in the reversed order and we just get some gibberish because the initial pointer might not be pointing to it points to the points to the start of string, so we need to read here, but instead we would be reading here, and that would be some random bytes. So clear direction flag, if I'm not mistaken, that's one of the reasons to initialize that as well. But anyway, I think it's good enough just to provide the code that actually works, and the matter of how deep you will get into to understand the details is all on you. So here we want to print next character, and here we want to read next byte from SI register. And yeah, by the way, what is the SI register? I forgot the abbreviation, so let's quickly search for that as well. SI register. Oh no, hold on a sec. We can look for it here within the registers. SI should be somewhere. source index, yeah, source index from source SI, source index DI destination index. So it's from source index register. Okay, and then we need to say compare AL with 0. So what this does, this compare, CMP stands for compare. So we need to figure out whether AL register. So and again, like the size of registers, it's another important thing to consider. So here we're working within the 16-bit mode. So let's say AX is a 16-bit register, but the 8-bit kind of upper and lower parts of it would be AL, which stands for A lower, and AH, which stands for A higher, or A high and A low. And still for, say, BX, that would be BH for the upper, and BL for the lower, like for CX, CH, CL. So when the register ends at H or L, it means that this is the 8-bit, kind of like 8-bit register. I'm not sure whether it's correct to say it like this, but anyway, so AL is the part of AX, but it's the lower part. AH is also the part of AX, but that's the upper, that's the kind of higher part, the upper part. Okay, so and it works the way with this specific interrupt hexadecimal 10 that the AL register is going to contain the current byte in the string. So AL would be containing G, then A, then M, then A. So load single byte increments the pointer. So SE points to this letter, and then every time we call load single byte, the pointer goes here, 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 and the next kind of letter the pointer points to, SI point, source index is pointing to, yeah, the source index is pointing to. This is gonna be stored into the AL registers. That is done somehow on the hardware level, okay? And eventually, there would be, when we increment from here, then we will hit the 0. So this is written as a string, but this is just a bit of a synthetic sugar for assembly. This might be presented in a format of bits as well, or doesn't matter how exactly, but we can just use a string here just for user convenience. Okay, so this AL is something that we're supposed to be printing to the screen, and it also would allow us to figure out whether we're done with the string or not. So one day, when we increment from here to here, the AL would contain 0, and that means that the string has already been printed, and we are done. So so here we want to match the end of string. Let's say it's better to call it 0 terminating character of the string. So match the 0 terminating character of the string. Okay, so if it is true, so if AL is equal to 0, okay, in this case we want to, there is the instruction called JE, which stands jump equals. So jump if AL is equal. So jump equals, so if it is equals, we want to jump to, let's call it, we'll create the label return. And here is the return label. And we just use the ret instruction, which stands for return. So we just want to return from from the procedure. Okay. So return if string is done, is over, is if string contains no more characters, if string doesn't contain characters anymore. Okay, return if string doesn't contain any characters anymore. Okay, hope this is okay. And now the most essential thing, we need to say int hexadecimal 10, and here we can say assuming ah is equal to hexadecimal e, like this. This int 10h would print a single character to screen in the teletype mode, by the way. So yeah, the teletype mode. So that's pretty it. Okay, and now we want to repeat this until we are done with all the strings. So here we just want to say jump to the next character, next character. So we want to repeat until string is printed. So print next character, repeat printing character until string is fully printed, let's say. Oh my god, guys, yeah, this is it. So this is all the code for this video, and now in order to run this we need to take a bit more effort. So I could have done this in the command line directly, but as far as this boot bin, so we need to make some cleanups, also like removing this unnecessary files, and also the matter of building the image. So I would rather create a new file. I'll call it run.sh, which stands for shell. I think that on Windows you also might do something similar using the batch file, right? So here, because I don't really want to type this every time, so new file, I'll call it run.shell. Okay, yeah, by the way, I need to make sure that the file can be executed. It's important. Yeah, hello execute as the program. Okay, so now, so the very first thing to consider, we want to assemble bootloader, and here we need to say -f bin and boot.asm, and then -o boot.bin binary. Okay, so this is the first thing to consider, and now let's just remove that for some reason. So let's open the folder, and just want to get rid of this. Yes, and now I want to run run.shell. Okay, and it should, it creates this binary file. Okay, so we delete this, so we run this again, and here we get our binary file. Good, so this works. Then the next step to consider, we need to generate floppy image. Again, like I call it floppy image just because of the size. So I'm using the dd command here. So say dd input file would be equal to, it's Linux specific only. If you're on Windows, you need to do this in some different way. I heard the utility called part copy might be useful for that, so some sort of an equivalent of dd for Windows. Not sure though. So dev 0, this allows just to fill the zeros to the output file. The output file would be, I'll call this floppy.image. Okay, and now the count, so the number of sectors we want to write. So I'll take this, this is the number of sectors in the 1.4 megabytes floppy image, but we will alter this, and I'll now explain the logic of how exactly this should have been done. And here bs equals 512. So the previous video we've been adding the missing bytes using the hack here like this, but just to add bytes in the binary executable. But here, as far as we're going to be bundle different binaries from all over into a single image, we're going to be doing this a little bit different way. But first of all, let's actually run this again. And here we have our floppy image, and this is the size of this kind of like floppy image. But it has all the sectors being zeroed. So just to show you that, so if I say xxd and then the floppy dot image, you see like we have all the zeroed segments, but we want the first segment to be kind of like containing our binary file boot.bin. Okay, we could have done this using dd as well, but I'm used doing this in a little bit different way. So I just subtract one sector, so it would be 79, and here let's say -1 equals to one sector for bootloader. Okay, let's say -1 sector for bootloader is going to be equal to 2879. So by the time we would be increasing the number of 512 byte chunks, files, call it however you want, we're going to be decreasing this count. So when we'll have our menu or even a placeholder for it, that would be 2878 respectively. So I hope that's clear. And now we want to, let's call it merge bootloader into floppy image, and then instead of merging only the bootloader, we'll be merging our binary files. So, but I'll change this later on. So merge bootloader into the floppy image, and here I'm using the cat command, which simply takes byte from one file and then from another and just brings them together. It's pretty simple. So cat stands for concatenate, if I'm not mistaken. So cat, and I'm taking my boot.bin and then the floppy.image. It doesn't matter that we have different extensions. On Linux, they don't matter at all. But both are just the binary files. So I don't know, probably we can call this bin as well, just for clarity, and like this. And then I want to output the result to well, we can call it flash.image, just to give an idea that it's going to be written on the USB flash drive. For now, we'll call it like this. Later on, we'll rename this to GameOS. Okay, so this is pretty it. And I think that, yeah, and one last thing to consider, we want to make some housekeeping. So housekeeping, well, it's just, okay, clean up files. So I want to say aram -f. I want to force if runs for the first time. So -f. I want to delete the boot.bin. No longer need this. And I also want to delete floppy.bin. Okay. And now, yeah, let's have a look. So it should automatically delete this file as well. So I'm running this run.shell file. So what we have the flash image, where this floppy image comes from. It's probably from, oh, yeah, just can delete this flash image. Yeah, okay, one more time. So having only boot ASM, should result in creating an image that we would be able to run. Okay, so yeah, this is the flash image. Now let's inspect this. So clear and xxd flash dot image. We don't actually need to wait until it shows all the stuff. We only need the first part. So we have the bytes being assembled into the machine code, and we have the boot signature. Perfect. So this is already a bare minimum setup to actually write to boot. That's pretty it. And by the way, I'm sorry guys, I just forgot one little thing. We obviously need to print this successful message. So in order to do this, we need to say move si. So si needs to point to whatever message we want to print. In this case, this is the success message. So after doing this operation, si would be assign the value of the pointer pointing to this point in here. Okay, so let's say point source index register to success message string. Strings first, strings address. Let's call it like this. It's very important to distinguish between the pointers and the data available at that memory address. So if you're not familiar with what the pointers are, you should learn that as well, because otherwise it's going to be a bit of a pain to code in assembly. Okay, so this is it, and then we just want to print our string. So call print string. And by the way, this sort of a thing, if we think in high-level programming manner, let's say, so this is kind of like give print a parameter, but we don't have this like argument, give an argument. We don't have arguments in assembly. We can't do that, but we can use certain registers to hold the values for like that treated to be as the actual arguments for a function. We're going to be reusing this later on when it comes to reading reading a single sector from the USB flash drive. Okay, so call print string. This is pretty it, and here we want to print success message. Sorry, success message to screen, and now it should print GameOS is loaded, and that's pretty it. Okay, let's call it actually GameOS. It's an operating system, man. Yeah, it should be like that. So get rid of this, and the very last thing, run OS image in the Camu emulator. Now this is optional. If you don't have Camu emulator, or if you have another one, you can use that. You can even, if you don't want to install the emulator, you can do this online using the online emulator. I will now show you in the just right in the moment how that works. By the way, now it's time. So there is a nice online emulator called Copy Shell. This is here we have the x86 architecture. We're going to be treating this as the hard disk drive. Okay, so if I go to here, and yeah, I didn't yet create that, sorry. So let's run it again. So now we have this image. Now I want to open this, open and start emulation, but it just takes a bit too long. Okay, just takes a bit too long, but anyway, we have GameOS is loaded, which is perfect. So you can use this as an alternative. So I'll probably put a link in the description below this video for this as well. So, but it's a faster way to use Camu. So I say Camu, and oh my god, I don't remember Camu system. Don't remember the how the command looks like. and it's important to use HDA because the flash drive is going to be treated as the HDA as well, even though that we're using floppy. So here I say note, we use we load image from HD, not from floppy, and this comes clear later on. Okay, so right, so this floppy is not even going to be seen later on. So in here I use GameOS.image. That's pretty it. And from now on, if I just call this run, it should run the camo, and we have our operating system being loaded. That's pretty it. So really lots of things to consider in order to have this, what is known as the Hello World operating system. But I'm sorry guys for the video takes too long, but this was absolutely essential to walk step by step through all of these things, especially the memory map. So from now on, for the next tutorials, we're going to be adding some things to the memory map to keep it clear what exactly is happening and where. That's one of the most important things. And also, what else? And also we're going to be adding some code to the bootloader. So we're going to be reading, so that would be one. So the next video will be dedicated to loading the sector from a hard drive, from the USB flash, I'm sorry. And then when we implement the menu to load our games, we'll then alter the bootloader a little bit. But for now, this is it from my side. I hope you loved the tutorial and learned something useful about the low-level assembly programming of x86 processor architecture. I'm sorry for not being expert in this sort of a field. I'm learning myself, but I'm trying to deliver this information as the beginner myself, just the most essential things that must know things, because otherwise it's just not going to be working. Okay guys, so thanks for watching. This is it from my side. Until the next time, and take care.